The topic of this problem is operational amplifier circuits, and the problem is to determine V out and I out in the circuit shown below. It's an op-amp circuit with a current source and a voltage source in it, as well as 3 resistors. V out is the voltage measured across the load resistance, which is the 6 kilo ohm resistor, and I out is the current which is flowing back into the op-amp from the output side of the circuit. So what we want to do is we want to use the ideal properties of op-amps along with our tools such as nodal analysis and mesh analysis to solve the problem. So the first thing we want to note is the properties, or are the properties, of ideal op-amps. First of all, we have the symbol for the ideal op-amp. It has an inverting and a non-inverting input. Each one of those has a current associated with it, and each one of them has a voltage associated with it as well. So there's a voltage at the inverting input and a voltage at the non-inverting input. And for an ideal op-amp, we know that the currents, both at the inverting input and the non-inverting input, are equal to 0. We also know that the voltages at the 2 inputs are equal to each other. So V minus is equal to V plus. We'll use these 2 properties, which are not the only 2 properties of ideal op-amps, but the 2 that are most important to this class for solving problems that are associated with linear circuits. We'll use these 2 properties to solve our original circuit. So let's do that. The first thing we want to note is the voltage at this node at the bottom of our circuit, which is the ground node. The voltage is equal to 0, which also tells us the voltage at the non-inverting input is equal to 0. Using the properties of an ideal op-amp, we know the voltage at the inverting input is also 0, which makes it a 0 volts at this node at the inverting input of the op-amp. So now we've used that first or second property of the ideal op-amp. V minus is equal to V plus. Now we're going to use nodal analysis, and we're going to sum the currents into this node which we've identified at 0 volt potential. And if we do that, we'll get something that involves V out as the unknown variable in the equation, along with other known voltages in the circuit. So we're going to do Kirchhoff's current law at node 1, and we're going to sum the voltage into, we're going to sum the currents into node 1. So if we start with a 4 kilo ohm resistor and we want to sum that current, it's going to be 12 volts minus 0 volts divided by 4 kilo ohms for the current through the 4 kilo ohm resistor flowing left to right into node 1. We also have this 2 milliamp source which is flowing into node 1 as well, so we're going to add the 2 milliamp source. In addition to that, we have the current which is flowing through the 3 kilo ohm resistor back into node 1. It's V out minus 0 over 3K. And we have the current which is flowing out of the inverting input, which we know is 0, our first property of the op-amp, ideal op-amp. I want to add it in there for completeness. And there's our sum. So this is Kirchhoff's current law at node 1. So we can see from this that we have an equation which has one unknown, V out, and we can solve for it. If we solve for V out, we end up with V out equal to minus 15 volts. Now we want to find I out. And I out is our current through, or current back into the op-amp. So we can use the node at the output, maybe we call this node 2, and we can use Kirchhoff's current law at node 2 to find that current I out. So this is KCL at node 2, and again we're going to sum the currents into that node. We could choose to sum them out of the nodes, but for consistency we're going to sum the currents into the nodes. So starting with the current up through the 6 kilo ohm resistor, we start with the voltage on one side minus the voltage on the other, which is 0 volts, minus V out. We know V out is minus 15 volts, divided by 6 kilo ohms. So it's 0 minus minus 15 for V out, divided by 6 kilo ohms. That's the current flowing up through the 6 kilo ohm resistor. We also have the current flowing left to right through the 3K resistor, which is 0 volts minus V out being a minus 15 volts, divided by 3 kilo ohms. And the other one we have is we have I out. And in fact, it should be a minus I out. Since we're summing the currents into it, we should have a minus I out instead of a plus I out for that current. And those are all the currents into node 2, and the sum is equal to 0. So we can, as you can see, we end up with an equation which only has one unknown, which is I out, and I out comes out to 7.5 milliamps.